Okay, so what we're looking at here are intermolecular forces. Now, from your covalent bonding, when we're talking about molecules, what do you remember about the forces? So if I've got a molecule, just say it's carbon dioxide, what would we say about our bonds? Strong intramolecular. And in fact, these are covalent bonds. Sometimes in phys we just said strong intramolecular forces. What was the other thing we said though? Weak intermolecular forces. So is everybody remembering this? This looks familiar, you've seen it before? Yeah? And so this was the way we explained our intermolecular forces for our molecules with covalent bonding. And then we threw in, just for a bit of variety, we threw this one in, didn't we? We threw in water. And what did we say about water? Yeah, we said water is a polar molecule. And what did that mean? Slightly positive, slightly negative. Which way around is it? Slightly negative oxygen and slightly positive hydrogens, but no net charge. Okay, so what that means is that the positives and the negatives have the same magnitude, and so they cancel each other out over if we look at the water molecule from afar, but if we look close up, then we know that the hydrogens have this slight positive charge and the oxygen has a slight negative charge. And everybody seemed to accept that and not really ask, well, is that special for water, or does it happen more often than that? Or, like what's so special about water, if you like, or yeah, everyone just sort of accepted that water was a polar molecule and we all moved on. Well, we're going to be looking into this bonding in more detail now, because in actual fact, what is this becoming like? What is this polarity becoming like?
Like ionic bonding?
Like ionic bonding, yeah. And so, you know how we said about our bonding types being just in these boxes? Well, that was a bit of a lie. And so we've got a bit of a continuum. So we've got covalent bonding. And we've got ionic bonding. And then we've got a little bit of bonding that's partially covalent, partially ionic as well. And this is where water sits, okay? So water is in this section here where we're saying it's not completely even sharing of electrons in the bond. It's somewhere in here that's headed towards ionic bonding. Does that make sense? That if we have 100% covalent bonding, then we have even sharing. And so an example would be any element. So if I look at, say, fluorine, then there's a single bond between them, and each nucleus from the two fluorine atoms has the equal capacity to pull on the electrons in the bond, and so the bond size is even on either side. Of course, it's the same atom, like it's an atom of the same element, and so there's completely even sharing, and that means there's no charge on the outside. Does that make sense, that's possible? But then we end up with things like water where we've got quite uneven sharing. And we can, so here, elements is an example. If we look here at our periodic table, so I think it makes sense that two atoms of the same element are going to share evenly within the bond, and so that means that neither side of that bond is pulling more or less on the electrons, and so they both end up identical. Well, what we need to look at now is the position of our elements on the periodic table. And do you remember how we said that fluorine was the most reactive element? And we said that, well, it's the most reactive non-metal, and we said that our most reactive metal was at the bottom of group 1. And we said that because the metals react by losing that valence electron, and because the valence electron is a long way from the nucleus, as we go down the group, then the nucleus has less attractive force on the valence electron, and it is easily lost. We said that the same reasoning led to fluorine being highly reactive because it requires one electron for noble gas stability, and so the ability of the nucleus to attract an electron is high because it doesn't have lots of layers of electrons around it to shield the impact of the nucleus. Do you remember that? Yep. Okay. Anybody not sure about that? So what this means is that fluorine is very good at attracting electrons. If we talk about purely attracting electrons, fluorine is the best element on the periodic table. It's most able to attract electrons. Attracting electrons is called electronegativity. And so fluorine has the highest electronegativity on the periodic table. And as we move down the group, electronegativity decreases. And as we move from right to left, electronegativity decreases. So our ability of our metals to attract electrons is low. They're what we would say is electropositive. They're more likely to be giving away electrons than attracting them. But if we just focus on this top corner here, because this is what we're interested in for our organic chemistry, we want to look at the relationships between these elements to see which one is going to pull hardest on the electrons in a bond. The fluorine will pull harder than the oxygen. Oxygen pulls harder than nitrogen. Nitrogen pulls harder than carbon. Carbon pulls harder than hydrogen, but not much harder than hydrogen. And so our bonds between carbons and hydrogens are fairly even. There's not really a great difference in the polarity, and so the bond is fairly even. But there is a difference here, and there's a difference between these two as well. Quite a large difference. That is why water is polar. Okay, because the difference has become so great that the pulling power, the electronegativity of the oxygen is much greater than the hydrogen. So it's pulling those electrons closer to it within the bond, and we're ending up with a slightly negative charge. Oxygen and chlorine are quite similar in electronegativity. Alright, so this is due to electronegativity. And you can see the table on the bottom of page 20 where fluorine is assigned this nominal value of 4. I don't know why the top of the scale is 4, but the biggest number on there is 4, and that's been assigned to fluorine. And you can see there that the oxygen is 3.4. So it's the next most electronegative element after fluorine. And then chlorine is the next one after oxygen. And then nitrogen and bromine are both there at 3, and carbon at 2.6, and hydrogen at 2.1. Right, so this is on page 20. Oh, sorry, 19. I'm looking at organic chemistry from 2015. Page change, sorry. So page 19. All right, so the important thing to notice for our organic chemistry is really the position or the electronegativity of oxygen and nitrogen. These are important ones for us. Okay, and so if you look on the next page, we're talking there about polarity and how now, rather than just talking about everything other than water as having just these weak intermolecular forces and just saying water is polar, we need to be a bit more detailed in our discussion of the attractions between molecules. If we have oxygen or nitrogen or our halogens present, that is going to impact on the attractions between the molecules. I'll put the halogens on there as well. Because of their high electronegativity and this uneven sharing of the electrons in the bond. Now I'll turn over to the next page, which I think would be 21 for you, the one that's headed Van der Waals forces. Is that 21? Yep. Okay. Because we're now going to split our weak intermolecular forces into 3 kinds of forces. First one are dispersion forces. And this is the terminology that is more accurate for the kinds of forces we were talking about in physical sciences. And these are the weakest of our 3 kinds of forces that we're going to talk about. And what happens is, so these occur in molecules and can occur with any bond in a molecule. But we sort of focus on our hydrocarbons. Okay, so we can have a simple hydrocarbon here. And what can happen is we form a temporary dipole. Now, what does temporary mean? Yeah, short time, not permanent. What does dipole mean then?
2 poles?
Yeah, 2 poles. So we're not going to have north and south. What do you think it might mean? Yeah, positive and negative. So with our weak dispersion forces, or our dispersion forces that are the weakest of the intermolecular forces, we set up a temporary dipole, which means that it happens for a short time, it's it's not permanent, and we end up with a positive and negative charge happening across a bond. So what can happen is, just say, a little bit of extra energy enters the system and we stretch the bond here. Okay, so bonds, we often think of bonds as sort of looking a lot like little dashes because that's how we draw them all the time. But there is the possibility they can move. Like we have movement, we have stretching and flexing of bonds. So a little bit of energy has entered the system here. The hydrogen has moved, or this bond is stretched a bit. Now we know from our electronegativity that the hydrogen has a lower electronegativity than the carbon, and so in the stretching here, this is going to end up slightly positive, and the carbon it's attached to is going to end up slightly negative, just for a short time. And if I've just got one molecule, well, that really doesn't tell me much about my interactions, because for me to have intermolecular forces, I need to be considering how this interacts with another molecule. Right? So that's just one. What happens if I have another molecule that's adjacent to it? I might do it this way. It's also had a bit of a stretch happen. So this is slightly positive. Slightly positive. This is slightly negative. Now I have the ability for these two molecules to interact. Because my slightly positive hydrogen on that molecule is attracted to my slightly negative carbon on the adjacent molecule. And so this is my weak dispersion. I'll just call it a dispersion force. From my temporary dipole. So we've got this, and then this will shrink back. The energy will maybe end up moving along the molecule, or maybe it's dissipated as heat. And then this attraction will end, and the molecules will no longer be attracted at that site after a moment. But we might end up with a stretching on another part of the molecule, which will then mean it's attracted at a different point at a different time. Now these ones are significant when the molecules are longer. So if I increase the length of the molecule, then I increase the chances of attractions from those dispersion forces. And this is the reason why our alkanes, so our alkanes like this basically have very low attractions to each other, and methane, ethane, propane, butane, all gases at room temperature. But by the time we get up to octane, nonane, decane, etc., they're liquids. And it's because of the length of the molecules then that there are more opportunities for them to attract each other with these dispersion forces, and there's enough of that happening, sort of like a bowl of spaghetti. if you think of long spaghetti compared to, you know, like short spirals or shell pasta, if you try and scoop out a bowl of shell pasta, you know, it's easy, it sits in the spoon. You try and scoop out a spoon of long spaghetti, and it's harder because they're all sticking to each other. Well, this is what's sort of like what's happening here, that the increase in the length of the molecule means that there's more opportunities for these interactions to occur. And because we've got more of them happening, that means that we need to add more heat to, or energy, to go from a liquid to a gas. Okay, so I'd have to add more energy. And the way we would normally express that is to say that it's got a higher boiling point, which we have this, just calling boiling point BP is